Good afternoon. Welcome to the third lecture in Lesson 2 of DC Circuits. This week we're going to be talking about series parallel or parallel series circuits. But before we go into that, we may as well do a quick review on series, the characteristics of series and the characteristics of parallel circuits. So, looking at the slide that I've got right in front of us here, I've got my first four characteristics of a series circuit, and we've got current is constant in all points of the circuit. Once again, as I've said repeatedly, we only have one current path. Since current does not slow down or speed up in different parts, it flows at the same continuous rate. Therefore, current has got to be constant in all parts of the series circuit. Three different resistors in this case. The total resistance of this circuit will be the sum of the individual resistances. The total voltage in the circuit is going to equal the sum of the individual voltage drops. We also know this as Kirchhoff's voltage law. And Kirchhoff's voltage law states that each resistance is going to drop a portion of the supplied voltage, so that in the end the total supplied voltage will be dropped by all the resistors in the circuit, and therefore if we measure or calculate the voltage drop for each resistor, they will equal the total voltage supplied to the circuit. And finally, power. The total power consumption is equal to the individual power dissipations of each resistor. And mathematically we can prove that. We can prove, well, based on the fact that current is constant, we can prove the rest. So, in this case, we happen to have 3 k ohms, 7 k ohms, and 10 k ohms. Therefore, using Ohm's law, where V voltage equals resistance times current, or current equals resistance over voltage, we can then determine that 10 volts over 10 k ohms, and for those of you still having trouble with the metric equivalence, that's equal to 10 volts over 10,000 ohms, is going to equal 0.5 milliamps, or 0.0005 amps. That's also equal to 500 microamps. So, 10 volts, oh, pardon me, that was 20 k ohms. My apologies. So that's equal to 20,000. 10 volts over 20 k ohms is going to equal 500 microamps, or 0.5 milliamps. Now, applying that to each one of my resistors to check the voltage drop, 3K times 0.5 milliamps is going to equal 1.5 volts. Going through the line, I've got 1.5 volts, 3.5 volts, and finally the 10 k ohm resistor at 500.5 milliamps, or 500 microamps, is going to equal 5 volts. A voltage drop. Add these voltage drops up. That should be 1.5 volts. Add those three voltage drops up, and you're going to end up with 10 volts. So, that's proof of Kirchhoff's voltage law, all based on the fact that current is constant in all points of the series circuit. Now power. Because we have an individual voltage drop at each resistor with a stable current, that means each one of these resistors is going to dissipate a specific amount of power each, or individually. So applying the power formula, power equals voltage times current. Well, for each one, we know the current at 0.5 milliamps. We know the voltage drop for each resistor. So calculating each one individually, 0.5 milliamps times 1.5 volts, I get 750 milliwatts, or 750 milliwatts. Oh wait, I was right. The point with the 0.0. Let me still delete that, and let me also delete this, and come back here again. So that's 0.75 milliwatts, or 750 microwatts, or 0.00075 watts. At R2, I have 1.75 milliwatts, or 0.00175. And at R3, I have 2.5 milliwatts, 0.0025. I can go straight to the total power. My 10 volts times the current, 0.5 milliamps, that gives me 5 milliwatts. If I then come down and add these guys up, you will find that I come out to 0.005 watts, or 5 milliwatts. So, mathematically, that works. Proves out the rules. And since we were able to mathematically, through these formulas, calculate calculate each value, if we have a single or more unknowns, as long as we know two characteristics of at least one resistor, we can determine the rest. Okay? So we know what the power is at a resistor. We know what the value of that resistor is. So calculating what each one of these resistors has in common. What does each of these resistors have in common? By calculating the current for one, we calculate the current for all. And if we calculate the current for all, we then can determine each characteristic of the resistor, and we can even determine, in this case, what the total voltage drop is. And, well, I work it out here. I will make this this PowerPoint, or this portion of the PowerPoint, is the Chapter 1, Chapter 2 S&P, or Lesson 2 S&P, and I will make that available in instructor notes so you can download it. And that way you will have access to all the calculations and be able to practice them on your own. But in this case, because R2 we have the most information, we can then use the power equation to calculate the power equation, along with, of course, the resistance, to calculate current. And we do that by first taking our power equation. So the power at R2 is going to equal the current times the voltage at R2. And then through Ohm's law, we've got an equivalent to the voltage, or the V in voltage, and that is current times resistance. So substituting the current times resistance into the power equation for voltage, we come up with the power at R2 is equal to current times R times current again, or I squared R2. So current is equal to, and we'll get rid of some of the scribblings here, current is equal to the square root of power at R2 over R2. So in this case we have 1.75 milliwatts over 7k ohms, and you'll find that I is equal to 0.5 milliamps. And then you can plug it in for excuse me. You can calculate what R1 is in this case by the voltage drop given at R1 over current. It's going to give you the value at R1. Then you can come up with your total resistance. And voltage, of course, is going to equal the total resistance times the total current, which will give you 10 volts. So there's playing around with series circuits just a little bit. Of course, we went through all of this last week with the difference in grounds, how they affect your reading via a meter. This ground point giving you a reference point. So if you've got a reference up here, but you're measuring from D to B, your reference, or the black lead on your meter, is going to be higher than the plus lead on your meter. If the negative lead is higher than the plus lead, you end up with a negative measurement. And that's why from B to C, the voltage drop there is always 3.5 volts, but our measurement via meter is going to measure a negative 3.5. Because B is our reference point, and it is a higher potential than D, our positive lead on our meter. Anytime we have to reference point B, and we're measuring either to C or D, we're going to notice we have a negative reading. So that's what this ground point here is going to do as far as references go. All right, then we talked about parallel circuits. And, whoops. So, parallel circuits, well, hang on just a second. There we go, somebody was tapping at my office door. Okay, parallel circuits. They have characteristics of their own. Where in a series circuit, we had a single path for current to flow. In a parallel circuit, you'll see we've got multiple paths for current to flow. And each one of those paths is connected to a common voltage source. So in a parallel circuit, voltage is constant at each branch. And each one of these is a branch of a parallel circuit. So voltage is constant at each branch of the parallel circuit. The total current, since we have multiple branches for current to flow, the total current is going to be the sum of the current flowing through each individual branch. The total resistance, well, it's not actually a total resistance, it's an equivalent resistance. So we call it resistance equivalence, because we want to be able to express it as the value of a single resistor. So instead of RT, that should be R equivalent. And the equivalent resistance is equal to 1 over the sum of the reciprocal of each branch. Or it'll be 1 over the sum of the conductance of each branch. And the total will always be less than the smallest resistor value. It will always be less than the smallest resistor value. So if you come up with an equivalent resistance that is greater than the smallest resistor value, you know you've made a mistake. Finally, the total power is the sum of the power consumed or power dissipated by each individual branch. So in this case, I've got 10 volts, and R1 is again 3K. Well, in this case, R2 is 3K, and R3 is 3K. Well, if we just go by the total current, the total voltage over the total current, well, let's calculate the total current for each one. So for each branch, our current will be 10 volts over 3K ohms. So each branch current will be 3.333333 milliamps. So my total current being 9.99999 milliamps. So if we look at we can round this up to 10 milliamps. We go with the sum of the current. The total current sum is 9.9999 milliamps, which is pretty much equal to 10 milliamps. If we calculate the total resistance, 10 volts over 10 milliamps, we're going to come up with 1,000 ohms. And then, well, we will go ahead and we'll calculate the total resistance through the sum of the conductances, or the reciprocal current method. Well, I didn't want to do that for that one. All right. There are multiple ways of calculating the equivalent resistance. The easiest and most common is the sum of the reciprocal, or the sum of the conductance method. However, in a case such as this, where we have 3 resistors all the same value, we would then take the value of a single resistor and divide it by the number of resistors, such as down here. The equivalent resistance for this particular circuit with 3 resistors, 3K each, would be 3K ohms over 3 resistors. The equivalent resistor is 1K ohm. So this is a special case where every value is the same. Well, let's come to one like this, where I've got a 3K ohm, a 7K ohm, and a 10K ohm. All right, we are still going to expect the resistance to be less than 3K ohms. So in this case, we take 1 over the reciprocal, or 1 over the sum of the conductances. And if you'll see, 1 over 333 microsiemens plus 143 microsiemens plus 100 microsiemens. Total is 1 over 576 microsiemens, or the total resistance for this circuit comes to 1.736 k ohms. REQ equals 1.736 k ohms. From there, it's quite easy. You can calculate each current drop. From there, how much power consumption each one has, and come up with the total power consumption and the total current. Since we know this value from these guys, I'm going to real quick do a calculation of 10 volts over 1.736 k ohms. So 10 divided by 1.736 equals 0.00576, so 5.8 milliamps. And if we look down here, well, how about that? I got 1.58 milliamps. If I do this calculation up here, I come up to pretty much 5.8 milliamps. Don't forget, when you do this actual calculation here, you're going to be going out several decimal points on each one of these, and these are rounded figures. All right. Solving for R3 in this situation. My equivalent resistance is 1.73551 k ohms. If I want to find out what R3 is, I can do it several ways. I can figure out what the current is by using Ohm's or the power equation. But I'm not going to be able to do that yet because I don't know what my voltage is, and I don't know what my resistance is. But I do know what my total resistance is. So here I have total resistance, so I can easily calculate R3, and from R3 I can calculate what the voltage is. So what you're going to find is you take the conductance of R3 is going to equal the conductance, the total conductance, so 1 over 1.73551 k ohms. So total conductance 173,551. Nope, sorry. 173.551, and call that 1 over x, which is going to equal 0.0005. We're going to call that 0.00576. And you'll notice it's to the -4, which is why my 5 is 4 decimal places in. Alright, that's my my total conductance. Now I'm going to subtract the other known resistor's conductance. So, where's my calculator again? So 3K, 1 over X, is 0.0003. And I want to round it to 2 decimal points. 33 minus 7K, 1 over X, 0.000143. Okay, so this should give me, this is G1, this is G2, and this is G3. So let's do the subtraction. Let's see here. Plus 0.000576 minus 0.000333 equals. So now I've got 1.00142857, and the list goes on. We're just going to take the reciprocal of that, and that will give us our resistance. This number is the conductance of R3. Take the reciprocal, and we end up with the value of R3. And that is 9.985K. Because we rounded up for these guys, we ended up dropping about 15 ohms, but that is pretty close to 10K, and I will take that as 10K. So since we know R3 is 10K ohms, we can then incorporate that into the power equation. So R3, the voltage is going to equal the square root of the power at R3 times R3, which is going to be 10 volts, which we knew from the previous equation what it would be. But that shows you that the conductance method is actually the most convenient and easiest to use method of solving for unknowns in parallel circuits. Alright, the two resistor special case, once again, you multiply, add, and then divide. So R1 times R2 over R1 plus R2. Once again, I'm going to leave you this PowerPoint in the instructor notes. You can download it yourself and play with it all day long. But here at least you have numbers to actually work through. Okay, series parallel circuits. Now, this is also known as a hybrid circuit or a combination circuit, because you've got components in parallel, components in series, and whether the overall circuit turns out to be a series circuit or a parallel circuit, well, that's something you got to analyze for. So in this case, we're going to be finding the total resistance for series parallel circuits. We're going to look at resistance strings in parallel. We're going to look at banks of resistors in series. And we're going to look at a combination of both going along. We're going to look at analyzing with unknowns. We're going to look at an archaic piece of equipment that's not used much anymore, but it is an interesting theory, and that is the Wheatstone bridge. And we're going to just talk about troubleshooting a little bit, because we kind of have the idea of troubleshooting on these already. Okay, series parallel or combination circuits, as we said, combines both series and parallel connections. And real world electronics is going to fall into this category. So we have to be prepared to use the theory or the characteristics of both series and parallel. This is why you have to get the foundation of these now. And by being able to analyze your way through the circuits, you're going to be able to apply, you'll know where to apply the characteristics of both. So as we know, series components, a string of resistors is a series. So series components form a string. Parallel components, when you have more than one branch, you're forming a bank. So the overall parallel circuit is a bank. The individual resistors are branches in that bank. Okay, this is a typical example of a series parallel. In this case, the overall circuit is parallel, in that you have multiple paths for current to flow. In the case of bank 1 here, you have a 3-resistor string. In bank 2, you have a 2-resistor string. Pardon me, branch 1, you have 3. Branch 2, you have 2. And here in branch 3, you have a single resistor. Now the whole idea, once again, is to get this down to the simplest form. Being able to express it as a circuit with a single resistor, and then using the information you gain here to expand back out to individual values. Okay, once again, this one is a series circuit with multiple parallel banks. So in this case, you have the current going through, but the current is going to split at this point and go through each separate branch. It will then come back together, going through R3, and it will split again, going through bank 1, and it will come back. So overall, it is a series circuit. The parallel banks we have to be able to express as a single resistor that will have a specific voltage drop, and it will have the overall current that gets split between the two branches but comes back together at the output of the branch. So this will be the equivalent of saying R1, R2, and R3 for most of the drawings that we've seen. And we'll see a little bit how to solve for these things as we go along here. Alright, well, here's where we're going to start. In this case, we have a series circuit. Now, how do I know it's a series circuit? Well, even though current is going to split here and here, it's going to come back together at point A, and I only have a single path through the next two resistors. So I have essentially a single path. This is like saying R1, R2, and R3. Being prepared to analyze R3 to an R equivalent. So in this case, I've got a voltage source of 1.5 volts. That voltage source is going to get split into two separate current paths. It happens to be one of our special cases in that both of these resistors are the same value. So I have two resistors in parallel. They are the same value. So using the special case for same value resistors, I take the value of 1 divided by the number of resistors. So now my R3 equivalent is going to equal 500 ohms. So I've got 500 ohms plus 500 ohms plus 500 ohms, or 1.5 k ohms. So my total current for this circuit is going to be 1.5 volts over 1.5 ohms, 1.5 k ohms, or 1.5 volts over 1500 ohms. And I'm doing this like I wouldn't know the answer. So I'm going to end up with 1 milliamp. So you see, I broke it down to simplest form. I determined what my equivalent resistance for this parallel bank was. Then I treated it like a straight series circuit, because that's what it becomes, to calculate what my total resistance was. So I expressed it down in the simplest form. And then I used Ohm's law to come up with my total current. So now I know what I've got here. I know what I have flowing into point B and flowing out of point A, but going through the actual resistors, you'll recall last week I called a parallel circuit a current divider, and that's exactly what it's going to do. At 500 ohms and a total current of 1 milliamp going through here, let me bring this guy back into the picture. 0.001 times 500 is going to equal 0.5 volts. So through this bank as a total, I'm going to drop 0.5 volts, which means I've got 0.5 volts across both resistors, because V is constant in a parallel circuit. So if I've got 0.5 volts and 1 k ohm, this resistor R3 here, 0.5 divided by 1000, is going to equal 0.5 milliamps flowing through this resistor. Since this resistor is the same value, and you can see two equal values. I've got 1 milliamp going in. I'm going to have half a milliamp of current going through each separate branch. But once I get back to point A, that will combine again into 1 milliamp. So R2 is going to see 1 milliamp, and R1 is going to see 1 milliamp. Meaning, this side is going to drop 0.5 volts, R2 is going to drop 0.5 volts, and R1 is going to drop 0.5 volts. 3 times 0.5 is going to equal 1.5 volts, so there's Kirchhoff's voltage law in a series parallel. All right, now once again, this is the Chapter 6 PowerPoint, so you can see we're going through each stage that we just went through, coming up with the total resistance. The parallel resistance shows you that special case, so that's the equivalent resistance of the parallel portion, and it goes through all that. All right, in this case, I've got a strictly parallel circuit, but one of the branches happens to have 2 resistors. So it's a series string. So that branch is a series string. So for this branch only, we're going to apply the series characteristics. So R1 is 8 ohms, R2 is 4 ohms. The total branch resistance for branch 1 is going to be 12 ohms. I've got 12 volts across that branch, so that means there's going to be 1 amp of current flowing through that branch. If there's 1 amp of current flowing through this branch at 4 volts, I'm going to have, oh well, never mind. At 4 ohms, I'm going to have 4 volts. At 8 ohms, I'm going to have 8 volts. That shows across this branch, I've got 12 volts. So that adds up. And I'm going to have 1 amp of current, as I said. Over here, I've got 12 volts across 6 ohms, which means there's going to be 2 amps of current. So the total current draw for this circuit has got to be 3 amps. This type of combination circuit is pretty much the easiest to look at. So, once again, the characteristics. In the series portion, current is the same in all components. Voltage across each series resistance is current times resistance, and the total voltage is going to equal the voltage drop across each resistor. In a parallel circuit, voltage is the same across all branches. I is still voltage over resistance, and total current is still the sum of each individual current for each branch. All right, once again, 1 branch for current, 1 branch for current, and another branch for current. In this branch, the current across these 3 resistors is going to be the same. For this branch, the current across those 2 resistors is going to be the same. It's going to be the same for this branch current, while this branch may be different. But for the overall branch characteristics, we're going to apply series. For the overall branch characteristics, we're going to apply the characteristics of series. And then for the whole circuit, we're going to apply the characteristics for parallel. So this is, if it is a parallel series, first you have to break down the series to express as a simple parallel, and then break down the parallel to its simplest form. Let's see if we got some more examples here. Well, in this case, this is a series parallel. That means my overall is a series, which means I've got one resistor, at least one resistor, either feeding straight across into the return, or I've got one down here feeding all the parallels. So one in line after all the current has come back together again. So in this case, instead of trying to apply the laws of the parallel or the series first, I want to express my parallel circuit into its simplest form. So what we're going to do, start with, is, well, we're going to look at our values here. We've got a bank with two branches. Both those branches are 10 ohms. So we can express this out in the special case. 10 ohms, there's two of them, 5 ohms. So now this branch is a 5 ohm resistor, or this bank, so far as we're concerned, is a 5 ohm resistor. So my total resistance for this circuit is 5 ohms plus 1 ohm, or 6 ohms. My current for the series circuit is then 24 volts over 6 ohms, or 4 amps. For this 5 ohm resistor, 5 ohms times 4 amps, my parallel voltage now is 20 volts, which means R2, 10 ohms, sees 20 volts. R3, 10 ohms, sees 20 volts. 20 volts divided by 10 ohms, that branch is going to see 2 amps. Same thing over here, that branch is going to see 2 amps. So I've got 4 amps going in, branches into 2 amps per branch, comes back together at point X, and I've got 4 amps coming out of point X. Going into my 1 ohm resistor, 4 ohms, or 4 amps times 1 ohm, it's going to equal 4 volts of voltage drop. 20 volts plus 4 volts equals 24 volts. So first, break down the parallel to its simplest form once you determine that you have a overall series circuit. Break it down to the simplest form, then apply your series circuit, and then go back and apply what you need to analyze your parallel circuit. And that's exactly what they're doing here. Okay, they tell you 24 volts and 4 amps, you're going to have a total of 6 ohms. So your 2 branches equaling 10 ohms each over 2 branches plus 1 ohm for R1 equal a total of 6 ohms. And then of course we were able to break it down from there. Okay, to solve series parallel combination circuits, you got to know which components are in series, which ones are in parallel, and is it overall a series circuit or is it overall a parallel circuit? Then simplify each of those circuits till you can reduce the circuit to its simplest form. And then do your basic equation solving and work your way out. Okay, in this case, I have single path, and then I branch off into two separate paths. So I know I'm working with a series circuit to start with. And since at the end, after all my current paths come back together, I've got one more resistor in line, it double confirms that I got myself a series circuit. So first thing I want to do is take care of all the, identify and then solve each parallel circuit. Well, there's one branch. Here's another branch. And I'm still in the same current path here. So this branch actually has another parallel series. I have my parallel there, and then another series here. So first, let's analyze this farthest out parallel circuit that we've got to work with. I got 12 ohms and 12 ohms, and I've got two identical resistors. So 12 ohms over 2, this is going to end up as a 6 ohm resistor, and it's in series with a 4 ohm resistor. So there's my 6 ohm, there's my 4 ohm. 6 ohms and 4 ohms, so these guys end up as 10 ohms. And they are in parallel with another 10 ohm resistor. So I've got parallel circuit of 10 ohms and 10 ohms, two resistors of 10 ohms. They're going to end up as a 5 ohm resistor. So now I've got a 30 ohm, a 5 ohm, and a 15 ohm. 30 ohm, 5 ohm, and 15 ohm. That's going to give me 50 ohm. So in the simplest terms, I've got a 50 ohm resistor. So 100 volts over 50 ohms, I've got 2 amps of current flowing here. Now I can start working my way back out. 2 amps times 30 ohms, I've got a 60 volt drop there. 2 amps across the 5 ohm, I've got 10 volt drop there. And of course, 2 amps across the 15, I got a 30 amp drop there. Now I can start expanding that circuit out. Okay, so now this is the same here. We can eliminate those two for the moment. This is the same as saying I've got 10 volts just across this circuit here. And I know that I've got 2 amps going into and coming out of points B and A. So if I've got 2 amps and identical resistors, well then I'm going to have 1 amp on this side. I'm going to have 1 amp on this side. Not to mention the fact 10 volts over 10 ohms, that confirms I'll have 1 amp. So 1 amp on each side. Now I can expand this guy back out again. So that's 1 amp and 10 volts. I've got 1 amp flowing through those guys. I've got 10 volts flowing through those guys. So 1 amp times 6 ohms, that's 6 volts. 1 amp times 4 ohms, that's 4 volts. 6 plus 4 equals 10 volts. So there you go. Got 60 volts, 2 amps flowing out of there, 30 volts, So that's how it's done. Oh, and then of course I've got this guy now. I forgot about that. So I've got a 6-volt drop across that resistor, but that resistor is actually that circuit there. So now I've got, oops, it would help if I turn my pen back on. I've got 6 volts there. 6 volts times 12 ohms, or pardon me, 6 volts divided by 12 ohms. I've got 0.5 amps there, which means I got 0.5 amps there. 0.5 amps times 12 ohms, that equals 6 volts, so that checks out. And there you go. Now we're worked out as far as we can go. So you see, the farthest out parallel circuit, to analyze that, you got to know what the voltage drop across the equivalent resistance was in order to work in that guy. And it is the voltage drop across this equivalent resistance. It has nothing to do with the input. It's just the voltage drop across that equivalent resistance. So, simplest form, and then work your way back out. Okay, we've pretty well dealt with this. Let's see here. They want to know what the V's are here. They want to know what the voltage drops. All right, well, you got 90 volts. 90 volts across 30 ohms tells me I'm going to have 3 amps at this point. Of course, since there's only one resistor here, he's dropping 90 volts. Come over here to where I've got 25 and 20. I've got 45 ohms total. 45 ohms, so I'm going to have, what, 90 over 45? That's 2 amps. So there we have it. Now, 2 amps, 25 ohms. V3 is going to be 50 volts, 2 amps and 20 ohms. That's going to be 40 volts. So now we have our unknowns covered for that. We didn't need to know the total resistance in this case, because this is purely parallel. Oh, and the total current, of course, is 2 amps plus 3 amps, 5 amps. Now, we could have found that by calculating the total resistance, but we didn't need to for these questions. Okay, once again, this goes to describe exactly what we just did. Okay, and we got that already. Did that? Okay. Here it's about my favorite series parallel circuit to work with. And it looks kind of confusing, but it's a perfect example of the sort of thing you got to do when you're analyzing these circuits. And basically, you are analyzing the joints and coming up with who's in parallel with who. So I basically just draw it out like a storyline, just straight across, starting with my negative terminal on my source. Okay? So, to start with, this is going to be in the end, a series circuit. I'm going to be treating it as a series circuit because After all the joints come together, I still have one resistor in line with my plus side. But now let's work the current paths. And my current path says I have 1, 2, 3 branches. So 1, 2, and 3 branches. My first branch gives me R5 all by itself. My second branch shows me R3, and R4 is going to come along at some point. So I've got R3 there. And then my third branch shows me R1 in series with R2. R1 in series with R2. Now, where these guys come together, I then have R4. And R4 remains in parallel with R5 until they come together here with R6 at the plus side. So you see I have 3 parallel branches, but I also have a couple of series in here. So let's start right here. This is R5, R3, R1, R2, R4, and R6. And you'll see, once again, if we look at our joints, there's point A, here's point B, and here's point C. All right, so R1, R2, both those are 8 ohms. R3 is 16 ohms. R4 is 12 ohms. R5 is 20 ohms. And R6 is 10 ohms. There we go. And coming in here, I've got 80 volts. Well, before I can solve the portion with R5 or get R4 involved, I need to take care of R3, R1, and R2. So I need to take care of this mini bank inside the overall parallel bank. So R1 and R2, they're in series. They're both 8 ohms, 16 ohms. They are in parallel with R3, which is also 16 ohms. So I happen to have 2 branches, value of 16 ohms, which these 2 branches together are going to be an equivalent of 8 ohms. This 8 ohm bank is in series with a 12 ohm resistor. So this bank and this series resistor is going to come up to 20 ohms. I now have this branch and this section, this bank and branch, both equaling 10 ohms. So together, or 20 ohms, 20 divided by 2 is going to equal 10 ohms. So now I have 2 10 ohm resistors in series. So my total resistance is going to equal 20 ohms. Okay, so now I have it down to its base. Now I need to expand back out from there. And since I have 80 volts and total resistance of 20 ohms, 80 volts over 20 ohms, well, that looks like it's going to be 4 amps. So R6 is going to see 4 amps. R5, okay, because R6 is going to see 4 amps, 10 ohms, 4 amps, it's going to see 40 volts. So my voltage drop there is 40 volts, so my voltage drop across this entire network here has got to be 40 volts. 40 volts divided by the 20 ohms of R5, R5 is going to see 2 amps. Which means from points A to point C here, on this lower side, I'm going to see 40 volts, and since it was 4 amps to start with, and I'm going to drop 2 of them across R5, I've got 2 amps across this entire network. And since this bank here and R4 are in series, that means R4 is also going to see 2 amps. So 2 amps and 12 ohms, 24 volts. So my drop across points A to B, is going to have to be 40 volts minus 24 volts, or 16 volts, at 2 amps. 2 amps going into A, 2 amps leaving B. Since these branches are equal, 16 ohms here and 16 ohms here, I'm then going to split that 2 amps. So R3 is going to see 2 amps, or is going to see 1 amp. And R2 is going to see 1 amp. So 1 amp times 8 ohms, I'm going to see 8 volts drop there. I'm going to see 8 volts drop there. 8 volts plus 8 volts, that's 16 volts, so that equals out right. And we can pretty well answer any question pertaining to this circuit. Once again, I got it down to its simplest form and then started working my way back out. It seems like a lot. It seems like it's confusing. And this is why we do homework. This is why we read our book and do exercises out of the book, as well as the exercises I assign for grading. Practice, practice, practice. I didn't get to where I could do this in one day. I had to practice the techniques. And once again, you have to know your characteristics. All right, the Wheatstone bridge. This is what they used to use to determine the value of an unknown resistance. So what you do is you've got, in this case, R1 and R2. That's a known ratio. And you have a rheostat in one branch. Now if you draw this out, you'll find this is a parallel circuit. And then you have your unknown resistor that you would install. Now in between, in the middle of the two branches, you install a galvanometer, which is a very sensitive current meter. And what it would do is the ratio R1 to R2 is going to produce a known current. And then your other side will also have a known current. Now, if these are out of balance, you will then have another current path to flow here, and the galvanometer is going to register so much current because one side will have more potential than the other. So you've got your unknown resistor, you have your variable resistor. You then adjust your variable resistor until the galvanometer reaches a null point, meaning there is no longer a potential difference between point C and point D. If there's no potential difference, there's no current flow. You then, because you know what the ratio is of R1 to R2, you can then know what the resistance is that your scaling resistor, or your variable resistor, and with that ratio known, the ratio of the unknown over the scaling resistor has got to equal the ratio of R1 and R2. Okay, so if the ratio unknown to scaling resistor equals the ratio of R1 to R2, then your unknown has got to be the value of your scaling resistor times the ratio that's already known. It's not used much anymore, but it's a neat concept and a neat way to think about parallel circuits. Let's see here. Yeah, and we will be taking another look at a Wheatstone bridge when we start doing a little bit of design of our own. Just not today. Let's see here. Troubleshooting, opens and shorts in parallel circuits. It's series parallel circuits. Well, they are going to show themselves in different ways. Okay, as we know, a parallel circuit, you short across a parallel circuit, you're shorting across the whole circuit. So in this case, our short is a switch here. So if we close that switch, it's just like running a wire and only having a 10 ohm resistor in series with your power source. So where this circuit, with the equivalent of a 40 ohm here and a 10 ohm, so 50 ohm load, at 100 volts, you'd have 2 amps of current. But if you get a short across your parallel section, you're going to see your current jump way up, because all of a sudden you've reduced your resistance way down from a 50 ohm load to a 10 ohm load. And it'll be the same, although not quite as drastic. If R1 shorted out, you'd go from a 50 ohm load to a 40 ohm load, and 40 ohms, it would end up a little bit higher than 2 amps. It wouldn't go quite as high as 10 amps, but your current would still shoot up. And that's showing the same thing. All right, in this case, they're showing still parallel circuit, still 80 ohms, and so the equivalent is still 40 volts, still 2 amps. Let's see what I'm looking at here. 40. Oh no, it's 60. No, there we go. 40 ohms, as it should be. 40, 50 ohm load, 2 amps, 20 volts, good. All right, so we got just the switch in line here. Now if we open that switch up, okay, all of a sudden, while still partially connected, there's still no place for current to flow through this resistor here. So you end up with a straight series, 80 ohms and 10 ohms, so a 90 ohm circuit. So all of a sudden your voltage is going to drop up, your voltage drop is going to jump up, as well as your current going down because you lost one of your branches of your circuit. So your resistance is going to jump up, your current is going to drop down. Just because you have this guy hanging out here, what that guy is going to measure, if we measure across points C and D, and if we were to stick a meter across points C and D, here, what we're going to measure is the voltage drop across R2. Yes, this resistor is still in the circuit, kind of, but there's no current flow through them. So all we're going to do is measure the potential across these points here. So let's see, 80 ohms and 10 ohms, that's 90 ohms. 100 divided by 90, it's going to be a little bit over an amp. So we're going to end up with an 89 volt drop at R2, and that's what we would measure out here. Okay, let's see, we already did that. And that's it. Like I said, it's going to depend on where you get the open, where you get the short. Of course, if you get an open out on this side, you're not going to have any current flow in the end because you killed your current path. But if you get a short on this end, with that guy connected, all you're doing is dropping this 10 ohms off. You still have a parallel circuit here, and that parallel circuit is still the equivalent of 40 ohms. Okay? And that 40 ohms, of course, you'll drop 80 volts across this point and this point. So across these two resistors, you're going to have an 80 volt voltage drop. Okay, that's pretty much all I have at the moment. And that pretty much does chapter 6. Read over the material. Do some of the examples in the back. Do some of the questions in the back where you have answers in the back of your book so you can kind of gauge where you're going wrong. And then ask questions. Like I said, this doesn't just seep in overnight unless you've had prior experience with it. But if you haven't had it, you got to practice. And I've had 35 years, 40 years of practice now. So the ease at which I'm doing it isn't necessarily the ease at which you're going to do it. Once again, Wednesday evening from 7 to 9 Central Standard, between 7 and 9 Central Standard, I'll be in my office, ready and willing to ask questions. You can text me, you can email me, send me messages on Blackboard. Anytime outside the office, you can still get hold of me. I'm more than happy to answer questions. But you got to ask them because I don't know what you're missing. So other than that, that's all I have. You guys have a good week, and I will talk to you later. Bye.